Oh.
Hello, people online. Can you hear me okay?
Yeah, it's all good.
Cool, thank you. Oh, where is everyone today? It's much quieter. Hello.
There you go. Fully charged.
Oh, thanks so much.
Don't forget to share screen.
Oh, yeah. Cool. Thank you. Okay, I just changed mics. Can you guys hear me online?
Yep.
Cool, thank you. Thanks. Okay, new people coming in. All right, so as I was saying, we're just going to go through this week's problem sheet to start off with, and then in the remaining time, we'll go through some more practice problems from the tutorial sheet. So I had a look through some submissions just to see if there was any like problems that a lot of people were struggling with. And I did notice a few. I'll go through all of them, but I'll just skip the ones that most people, I'll go quickly through the ones that most people seem to be fine with. So, hello. So for the first question, I hope this is, oh, you'll notice, so my writing size was so all over the place last week. So I've got a dotted background this week. So it's going to be consistent, hopefully, fingers crossed. If this gets too small, apologies, but maybe bring up the PDF that you guys have, because yeah, the size just doesn't work quite well on here. Okay, so question I. This is kind of a word question in a way. Does anyone want to like shout out the answer? Here we go. Nearly everyone got this right, so you're probably correct. Yep. Yeah, so the operator is equal to its conjugate. Is that what you mean? Yeah. So the operator, let's call it H, is equal to its Hermitian conjugate. Yeah. No one seemed to have a problem with that. So let's go to the next one. There was a few, most people like had the right idea here, but maybe the wording was like not super clear or stuff like that. So basically, why do we require observables represented by Hermitian operators? This is because we want real observables. So keyword being observables. Some people just got the wording a bit mixed up. So we talk about observables or eigenvalues. Someone is unmuted. Just gonna mute you. So yeah, just wording in physics has to be quite precise. Sometimes it might seem like you're saying the right thing, but your words might be quite slightly off. So just make sure you think about your wording and make sure it's like you're saying the right things. Okay, so next question. How could you know at first sight whether an operator is Hermitian? So there was a little bit of confusion here. I think, yeah, just more in terms of people not being super clear with their answers. So, oh God. So a good answer for this would have been, okay, two things. One, the diagonal elements are real. And two, the symmetric off diagonal elements are complex conjugates. Yeah, so some people wrote something along the lines of off diagonals are complex or off diagonals are complex conjugates, but that's sort of missing an important chunk of the information there. So just make sure you think about whether your sentence is complete and actually saying what you want it to say. So you could write that in the words that I just said, or you could write it in math. It's best to write it in both, I think, just to be really clear. So what I just said plus that would have been a great answer. Okay. Next question. Okay, most people got the next one right, so I'll just go through that one quickly. So we're just proving that this operator is Hermitian. So if it's Hermitian, we have to prove that, like, this basically. So let's find the conjugate of T. So that's going to be the complex conjugate of T and then transposed. So let's do the complex conjugate first. So all the I's just turn negative, like switch signs. And then we still need to transpose this. So we just flip it around. Okay, and then you can see that that's equal to the original matrix. So yeah, therefore it's Hermitian. Okay. We can go to the next page. So where were we? So yeah, most people got that correct. And the next one, most people did correctly as well, but I'll just go through it. So this is just a bit of like linear algebra, finding the eigenvalues of T. So we write our auxiliary equation. If you're unfamiliar with this or you struggled with this, just go back to your linear algebra math course or just do a bit of practice finding the eigenvalues. Or also just let me know later when we're like working and I can explain it to you in more detail. So just finding the determinant. and setting it to 0. Yeah, now we're just solving this for lambda. So both of these are 0, which gives us lambda equal to -1 or positive 2. Okay. Did I put the question number here? Yes. All right. Yeah, most people didn't have a problem with that. But the next one, a lot of people overcomplicated this. So, sorry, I keep losing the questions. So the next question was write T in its diagonalized form. So yeah, there's a really simple way to do this. You can in like one step, basically, without like really any calculations. A lot of people really overcomplicated this and end up getting it wrong. So I'll just show you the simple trick. You've probably forgotten this from your math course. So you just have to remember that the elements of the diagonalized matrix are its eigenvalues. So you just write down the eigenvalues. It could be either like this or like this. And you can see like based on what we said in this question with the question 3, triple I, the two conditions for the operator being Hermitian, you can see just by looking at it that this meets those conditions. Cool. Is there any questions so far? No. Cool. Oh, yes. Which 3 matrices, sorry? It just wants you to find the diagonalized form. So you can do that in any way you want, I guess. Oh, I know what you're talking about. The really complicated thing where you like switch all the rows around and stuff. Yeah, that's the long way of diagonalizing a matrix. So yes, you could have done that. And if you got the right answer, that would have been fine. But that's extremely tedious. So this is probably a much easier way of doing it. Yeah, since you've already got the eigenvalues. I hate that way. I actually don't think I've ever used that. Like it's just so complicated. You never remember how to do it that way. Okay, let's go to the next question. So this one we're up to. Okay, so a lot of people had a problem with this one. In fact, I think I didn't manage to look at everyone's, but yeah, this one confused a lot of people. The main reason being that most people used the undiagonalized matrix to find the eigenvectors. You can do it like this, like it's not wrong, but it's just really complicated. And I think it was a combination of using the more complicated matrix and forgetting some linear algebra techniques. So actually maybe it's a good exercise to try and do it both ways, but yeah, use the diagonalized one and then try and do it with the non-diagonalized one and you should get the same answer. But yeah, in this case, because we have our diagonalized matrix, it's just a lot easier to use that. And yeah, it'll make the math a lot easier and harder to make mistakes. So I'll just go through that. So let's start with, which question is it? VII. So let's start with our eigenvalue 2. Using our diagonalize, okay, wait. Firstly, let me just remind everyone of what we're doing. So write the eigenequation. So this is our operator or matrix. These are our eigenvectors. Sometimes it's good to just have this picture in your head so you don't get confused when you're doing the math. This is our eigenvalue. Value. By the way, I can't spell, so forgive me if I spell things wrong. Okay. So for lambda equals 2, let's plug everything into our eigenequation. So we're going to use our diagonalized matrix form because it's just going to make our life so much easier. It's got lots of zeros in it. That's why it makes things easier. Okay. And we'll write our eigenvector with our unknown elements. Our eigenvalue is 2, and then here's our eigenvector again with the unknown elements. Okay. And now we're just going to do some matrix multiplication here. So we'll have 2a plus 0 times b, and we'll have 0 times a minus b. And then we can put 2 into this vector as well. Oops, that should be a. And now let's write this in a simpler form, just going through it slowly. So we have 2a minus b is equal to 2a, 2b. Oh no, even with my dots, I think I've started to make my writing massive. Let's scale it back. Okay, so remembering how to do linear algebra, we have this is one equation and this is the other equation. So 2a equals 2a, and we also have minus b equals 2b. So the only way the second equation can make sense is if b equals 0. And we can set a to be anything, but the simplest convention is to have a equals 1, and then these equations work. So these are the elements of our eigenequation. And now let's do the same thing for the next one. Is that can you guys read it if it's that big? Okay, this is a good size. I'm just going to leave it like this. Okay, so we had -1. I'm going to go through this one a little bit quicker because it's basically the same thing. So we're putting in our diagonalized matrix. And this will give us 2a and minus b again. And now we're going to have minus a minus b. So this will give us these equations. 2a equals minus a and minus b equals minus b. And using the same logic as before, we get these elements. So in summary, our eigenstates for lambda 2 equals 2 is, let's call it x 1, 0. So it's putting those a's and b's in. And then for lambda equals -1, we have x. Maybe I should call this lambda 1, lambda 2. Zero, 1. Yes. Sorry, can you say it again slowly, please?
Those are the arguments of devil's maths of 2, 0, 0, -1.
Yes.
But they don't work as arguments for the original matrix.
They should do.
You can check it. They don't. They won't
Okay.
advise you on math.
I can check it later. Yeah, I'll check it later once I've done this. Yeah, they should work. But yeah, I'll try it in a bit when everyone's doing their own thing. Okay, so that was all of question 1. Question A, sorry. Let's move on to question B. They don't have any questions so far? Cool. So this was another question that a lot of people either didn't get quite right, or maybe they just weren't super clear with the answers. So I'll just give you like a good answer. So basically, what does the completeness relation mean, and why is it important to quantum mechanics? So it means that all the possible outcomes of a measurement have to equal 1. And this is important for making probabilities make sense in quantum mechanics. So basically, I'm sure you know that probabilities have to add up to 1 when you're talking about like a single event, I guess. Yeah. Yeah, that was kind of like the thing that was missing out of a lot of answers. So it's quite simple. But yeah, easy to miss. Okay. So last question, everyone got this right, I think. Basically, we're just showing the completeness relation for this system. So we have the eigenvectors for up and down, and we have this equation for the completeness relation. So that has to equal 1. So let's sum up our eigenvectors, our eigenstates. Wait, don't need that. Okay, so we're summing up plus down. So just doing some outer products, which if you're not familiar with, there's a couple questions in the tutorial which go over these. Hopefully we get to those today. So you're now just adding these up, and you may recognize this. This is the identity matrix, which is essentially 1 in like the matrix equivalent. Yeah. Great. So that's the last question. Did anyone have anything they want to ask about this? Okay. We have an hour. Yeah. So do you guys want to take like a quick 5-minute break? And then we'll spend the rest of the class working through tutorials stuff. Yeah, a lot of it's but one of them and I think 5 Yeah, why does it?
Oh, that's just, yeah, that's just. I just got rid of those.
No way. Oh.
Yeah, because it's just. Figuring out
Yeah. I thought that's small.
Like I had a different.
Like animation.
I've told you.
It's just like all the. But like if they ask you. Yeah.
I think the problem with this is that it's not an item.
I just, I did it. Oh, no, no, that's. Oh, yeah, I mean, actually. Yeah.
So it should be.
It's, if you're working with a standard. It's like the way the matrix is really.
So you had like
Yeah, it's just.
minus.
What these are your basis. Matrix itself.
It doesn't work because now it's a matrix.
Remind.
Yeah, it should be.
Yeah, but isn't the other matrix? Okay, so that's all.
Oh.
Yeah, and you get like. One, two, three,
Oh.
yeah, that would be-
Same equation.
I'll try my light.
One mistake I did notice, it wasn't yours, but like, which may have been the common mistake, is when it came to actually turning this into equation.
Very out of my.
Because with your method, you end up with
Oh, yeah.
and basically the equations, and that didn't happen, like some error. When that was being turned into equations. So that might. Oh, yeah, you just need to put an item.
Like I remember from. Normally.
Talked about this. And I have
Especially like.
But I'll try.
I'm sorry, I really.
I'll try to do this.
But it's not like.
Yeah, I mean, if that doesn't work, try your matrix still. It's not.
Yeah.
Do you connect it?
Yeah, like you just do the.
Yeah.
Yeah.
Yeah. You should still, you should be able to do that.
I will do that.
Yeah, that's not sure. That's.
No, I didn't. No, I didn't. I just.
I've heard like.
Like this side, two backwards. And then this element. So this is essentially something.
Yeah.
Yeah.
But in this case, that. In your case. Like we get something like. We get you have to do some things. I think that was one.
I'm ask about this. Yeah, like it's like I do different. I do and like when I go to class, I go up to like generalize different special. But they actually go and check like but like you get one solution with elimination or minus solution. But I do those values. I don't get the I get something different. It's not the thing I have to hear. I'll get like 1 times 1 is 1 and the side times 1 times 1 is I. So like those answer like I can throw this.
Okay.
Okay.
Yeah.
Yeah, because
I didn't really. So much. Like, it makes sense if you say.
Okay, everyone, let's get back. But we're now in the part of the class where I'm gonna like set you up with some tutorial questions in a second, so you can keep talking in like a couple of seconds. So let me just open this up. So last week we got up to last week, I believe we got to question 2B. Did anyone continue this at home? Anyone? Just put your hand up. It's okay. No judgment. Okay, so most people didn't. That's cool. So let's like kick off where we were then. I think I went through the solution of A and B. So let's keep going with C. And yeah, I'll be walking around to answer your questions, and I'll get through hopefully a couple of solutions. But yeah, same as last week, I would rather everyone is sort of on the same page and understanding things than to be like rushing ahead and getting through as many things as we can. So we'll go as slowly as we need. And also, if you have questions about the assignments, just let me know. I can't answer questions about marking because I'm not marking it. But if you're confused about some of the questions and the solutions, just let me know and I can try and help. All right, go for it. We'll start going through solutions in like, I don't know, 10 minutes maybe. We'll go through 2C. Oh, I meant like sorry, oh my God, scary word. I meant the problem sheet that we just went through. Yeah. Sorry, I just triggered you. Holy shit. Sorry about that. Okay, don't forget. So to answer your question, it was actually a really good question. So I remember my linear algebra, the eigenvectors will not be the same if you've changed the matrix, because now you have a different basis for your matrix. So the eigenvalue will be the same, but the eigenvectors will look different. And you can transform between them by doing a basis change. Probably too technical, don't worry about it. But yeah, that's why if you try to use the eigenvectors here that I got with the diagonal matrix on this matrix, you won't get an eigen equation that works. So your eigenvectors will look different if you've used this matrix, but you should have the same eigenvalues. So to check your working, to check if you got the correct eigenvector, you have to make a eigen equation and just check that it works with your eigenvalues. Said eigen so many times, yes. Yeah, if you get the correct one, yeah. So you can check, probably actually it's a good learning opportunity. You should check your answers. So if you want to make sure you got the answer correctly in this kind of question, take your eigenvector that you calculated back to the matrix and make sure it spits out your eigenvalue, and that all works. Yeah, great question. Yeah, I guess, yeah. Then yes, I guess.
So we need solution.
Yeah, it's correct. I haven't got.
Okay. So if I can transform this, then this is all.
If that's what you want. Okay, let's do some physics. Okay, we're now no longer working on this. So question 2C. We're showing that alpha star B and gamma star delta must be purely imaginary. So from our equations in the previous question, oh, I should label this 2C. So we've got alpha star beta plus beta star alpha equals 0. In other words, negative, sorry. So let's let this be complex, some complex number. And the other side of the equation is its complex conjugate. So that means this will be x minus iy, because maybe I'll step through that one. So just write that out more clearly. Okay, so that means that we have and cross out the x's, and that means we have and also cross out the i's. That means we have y equals minus y, which only makes sense if y equals 0, which means there's no imaginary part. So yeah, therefore alpha star beta and beta star alpha have to only have oh, sorry, I made a mistake. This is what I get for not following my own notes. Let me do this again. Okay. Beta star alpha equals this. Right, I forgot the negative sign. That's what I did. It's always the negative signs. Okay, that makes more sense. So yeah, now these terms cross out. And we have x equals minus x. So x has to equal 0. Which means that alpha star beta only has an imaginary part. And yeah, same thing for delta, gamma star delta, basically.
Like different definition, they do have real animals, but the universe is not the same for people like how you say that's animals must be real. It does not say imply that like a regular solution. Yeah. So when you look at like those matrices are not equal, they doesn't equal. Yeah. So yeah, those matrices are not equal, but they're not the same eigenvalues. Yeah. Okay. That makes sense. Yeah, I think so. I'm trying to check it, and I don't find it most. Yeah. Anyway, yeah, so we can think eigenvalues because one of the kinds of eigenvalues is stuff that you measure. Yeah. So that has to obey normal physics rules, right? So using the division, yeah, so the non-emission operator has not measurables, then I don't see how it could be made into a Hermitian operator with real measurables, because then you'd be changing the real outcomes. Yeah. Okay. Oh no, we have 5 minutes left. It's okay, no one's coming in, so I'll just go through the next one. How did everyone go with that? Cool. Go to another page. Actually, no, I think it's probably more beneficial if, oh, does anyone have any questions they want to ask me? Sorry, I didn't get a chance to go around because I was thinking about this good question. Did anyone have any specific questions they wanted to ask before we finish up, or do we want to just go through one more solution? No questions? No questions? Okay, we'll go through one more solution then. Okay, so use your argument in C to show that alpha and beta, as well as, oh, you guys don't have the tutorial questions, sorry. So use your argument in C to show that alpha and beta and also gamma and delta cannot both be real. In other words, show that we must go into complex amplitudes for these. Okay. So 2D. So yeah, suppose that alpha beta is purely imaginary, and let's say alpha and beta are unknown, like complex numbers. So that means we can have alpha beta equals okay, and then just expanding the brackets. I'm going to skip this step because we don't have much time. Eventually we'll end up doing some algebra. We'll get this form. Okay, and this is alpha beta. And remember that from the previous question, the real part doesn't exist. This is our x from the previous question. So this is equal to 0. Does that make sense? Everyone like following that leap of logic? X. Oh, sorry, this should be negative sign. Yeah, thank you. Is that what you meant? Yeah. Sorry, I forgot to conjugate it. Okay. So that means we have yeah, so we have this equation. And then just looking at this equation, that means
if y and y dash, if y and y dash is not equal to 0, then y times y dash can't be equal to 0. Oops, sorry. Does that make sense? Maybe I should write out this equation. Yeah. Essentially, the only way these can both be 0 is if these can both be 0 is if these are both also 0. So everything has to be 0. So in other words, we need these to be non-zero. Yeah. Sorry, I've rushed this one. I think maybe we can come back to this one next week. It's never a good idea to rush. Yeah, okay. We'll do this one again properly. See you guys next week. Slay. See ya. Merry Queersmas. Hey. Yes. About what, sorry? Say it again. Yeah.
Measure matrix matrix two real eigenvalues.
Yeah.
Then
Thank you.
obviously in right, if a non-measure matrix has two real eigenvalues,
Yeah.
and if
Non-Hermitian matrix that has two real
the two megaball points.
I would say like
Is it possible for that circumstance to exist? It's very much possible, right? Like
I can't tell you definitively. I don't. Thank you. I don't know that. I don't know the proof for that. Yeah. Sorry, I can't tell you.
Alright, so maybe.
I haven't done 2B, and I have no idea what it's done.
2B? What's 2B? Oh, in the tutorial. Oh, the one that we rushed through already and saw through. Yeah. Okay. Go through the solution. I can't remember. Maybe it's 2B. It's very similar. Like you make this, start with the sandwich. So maybe like, yeah, start with the sandwich and go from there. So we're doing similar sandwiches to here, except the inside states are going to be left and right rather than up and down.
Yeah, it's not the front of it. So I
Yeah.
can like go through it if I forget it.
Oh, hey. Ready? Yeah. Thanks. No worries. Okay.
We had a question about question 7.
Okay.
Like, why can't we use like the original matrix?
Oh, no, you can. You totally can. It's just going to be really confusing.
But when we did our eigen like vectors.
Yeah. Yeah, so that's what I was saying before, that guy's question. You've got like a different form of your matrix. You're essentially going to have, you have like a different basis. Complicated, don't worry about it, but it basically means that your eigenvectors.
So this
Are these right?
I don't have this answer, but like, yeah.
so this matrix is not the same as that matrix.
No, it's the same matrix. It's just written in a different basis.
Oh, okay, I see, so it's written in different places. So that
Yeah.
means the eigenvalues, but
Yeah.
the eigenvalues itself.
Yes.
Okay.
Yeah.
What does that mean, like?
Different basis.
Because it just means like what, the state you're measuring, the measurement will be the same, but then the vector will be different. What does that mean, like, in terms of like quantum speeds?
Well, it doesn't. You have to remember that the only thing that matters at the end of the day is the eigenvalue.
The actual
because
measurement.
That's what comes out as your observable.
Oh, okay.
So everything else can change. But the only other thing that's connected to reality, which is your eigenvalue,
That's the actual measurement.
that can't change because that's related to a physical, like tangible
Okay.
result. that
So
you're
the
gonna get.
eigenstate is like not as important as the actual eigenvalue itself. then?
Yeah, I mean, like they're all important. like,
Yeah, obviously.
but like that, those kind of things can shift and change because they're not directly connected to like reality, if that makes sense.
Yeah.
Yeah,
Okay.
Thank you.
no worries. Thank you, everyone.